So thank you very much for that introduction and the overview of the Hasso-Plattner-Institute. It's a pleasure to be here today, opening the first of what I hope will be a series of passionately interesting workshops on a subject that is very close to my heart. And today I wanted to talk a little bit about part of the work that my group at Viewpoints-Institute is doing that is directly relevant to the subject of this workshop. So this is a small part actually of what we are attempting to do to change the world for the better. But over the next 5 years, our big question is really for a typical user of a personal computer today, really how hard should it be for computer scientists to connect that person via their keyboard, their various input-output devices, sound, their big screen, etc., through the small variety of tasks that people typically perform on a computer. Most of these tasks just being an electronic simulation of old-fashioned media. With a few 21st century frills thrown in, such as transferring documents electronically from one place in the world to another at the speed of light. How hard should it really be to connect that person to the technology? And are the systems that we are building today, and are the systems we are using to build those systems, really the ones that are best adapted and most efficient to accomplish this task? So we'll see a little later in my talk about how the ideas of self-sustaining languages and self-sustaining systems might help us with this. But one of the other big problems that we're up against really is the management of complexity. And this isn't unique to the domain I just described, but in every scientific endeavor, I think at some point or another, people come across a barrier, which is the complexity of a system that can be understood by a single person or by a small group of tightly connected people. And this is a problem that has been known about for a long time, probably from the late 50s onwards. People were tackling exactly this problem. But it was summed up perfectly by Edgar Dijkstra, who most of you will recognize the name of, who posed the question 7 years ago in the communications of the ACM. To what degree is the complexity in our systems actually intrinsic in what they do, and to what degree is that complexity just accidental? And can we really take out the intrinsic intricacy and remove that from the accidental intricacy, the complexity, and throw that complexity away? So that really is the essence of what our project is about. So another way to look at this is that we are thinking about powers of meaning and how to optimize the way people can express and can instruct a machine what it is, the intention of that person's programming or that person's interaction with the machine. So how much can you tell a machine to do with how little expression? And the better that ratio, the better the expressive power of the system that you're using. And so two extremes that are interesting to look at. If you take the whole of the legal system in the United States, which I admit freely is a disaster, and you codify it, you print it out on paper, it suffers from being a case law system, meaning that for any particular situation, the first job of the 15 high-paid lawyers is to look through the history of cases and try and find one that's similar, and then it's a foregone conclusion. But if you print all of that history out and all of the rules surrounding it, you end up with about 3 cubic miles of paper, which is a lot of paper for one person, let alone a team of people, to understand. At the other end of the spectrum, let's take a very well-known piece of physics, which is electromagnetism, and all of electromagnetic phenomena can be expressed in just 4 tiny equations. These are those tiny equations. So the lights that are illuminating the room, the projection onto the screen here, the thing that keeps your beer cold in the refrigerator at home, everything that is involved with light, with electricity, and with magnetism can be expressed using these 4 equations. They may not be directly applicable to your everyday life, and there may be a lot of history and a lot of talented people that were behind the codification of these rules. But in the end, the power of expressivity here is far beyond anything that computer science can manage today. So we'll come back and look at a few more interesting properties of these equations later. But coming back to the computer science example, at one extreme we have US case law, at the other extreme we have physics, Maxwell's equations for electromagnetism, and I pulled some examples from Wikipedia recently of the complexity of various systems that most of the people in this room will be familiar with. I was surprised actually to see that a Linux distribution, a very popular one, is more lines of code than Mac OS X, but I guess that's progress in the open source community. It's surprising as well that Mac OS is actually more lines of code than Windows Vista, but we all know that Vista doesn't work, so maybe that explains this as well. FreeSB, a very nice system, in relatively speaking, for computer science terms, a very, very small amount of code. And then we look at the typical application. OpenOffice, the freely available suite that does what Microsoft tries to do, is about the same number of lines of code as an operating system, which is in some ways a little surprising. Then if we look at the middleware, the tools upon which we are building these applications, and we take a popular user interface graphics toolkit, GTK, we see that it represents about 500,000 lines of code. Maybe a little over, 2/3 and I actually found one intelligent thing that William Gates said, which is that if we measure our progress as a scientific community by how many lines of code we are writing, it's like asking an aerospace engineer to optimize his design by increasing its weight. So let's put some of these lines of code counts into real-world terms, the kinds of terms that you or I could easily imagine, because when we start talking about 9 million lines of code, it's very difficult to imagine what that means in everyday experience. If you were to read a journal article, a scientific article, maybe 2,000 lines is a typical size for that article. 20,000 lines would be a typical novel or a typical textbook today. 200,000 an encyclopedia, maybe a multi-volume encyclopedia. By the time you're up to 20 million lines, there in the middle of the operating system size, you're looking at a pretty good private library, 1,000 books worth of information, and already you're reaching, well beyond the limit of what one person can reasonably expect to master in their lifetime. Be familiar with, okay, but master so that they really own what is expressed inside that work, probably not. And by the time you get to the upper limit, Debian Linux, for example, you're looking at a fairly sized community library. Now, bringing this back into the context of our project, we think that 20,000 lines, a typical textbook or a novel, is probably about the right order of magnitude for expressing the interaction of a person with their computer doing their everyday tasks, with those frills such as hyperlinking and electronic transfer of documents thrown in. And what's very important here is that size in the left column there ultimately determines your accessibility to the knowledge that is embodied in those lines of code, or those lines of prose, those lines of equations, whatever they happen to be. The fewer those lines, the easier in principle it is for you to master the knowledge in there, and therefore to, in some sense, own that knowledge and to be able to work with intimately and even modify the knowledge that is in there. So this is a picture, really, a broader picture of what we are trying to achieve. Along the bottom, you have a spectrum starting with physics on the left, the power that makes the computers work through the logic gates and the operating systems, the programming tools, to the user on the right, and then maybe even beyond the user, to some of the processes that are actually occurring when we interact with the computer. So not just applications, but also learning, the use of a computer as a third party in a learning process, or maybe even as the pedagogical topic itself, if the topic in discussion happens to be computer science. And our approach is to try to create our 20,000 line system by finding the few, and we're getting into the self-sustaining ideas now, the few minimum, the core concepts that are involved in as broad a spectrum as possible within this diagram. So can we find concepts that are very simple, very powerful, and scale immensely well, such that they are applicable and efficiently applicable both on the left and on the right. On the left, where we're talking about the implementation of our systems and what actually makes them tick, what connects them to the silicon underneath, and then on the right as well, the interaction, the teaching through computers, the interaction with computers, and the construction, the organization of the applications that people use to interact with those computers. And it may be a little hard for you to see here, but the area in the middle is where some of these abstractions exist. And it's not at all clear yet what this collection of abstractions will be. We have 5 more years to try and discover this thing. But the magnitude of this task is illustrated nicely by one of our favorite cartoons at the top. And for those who maybe can't read this, we have maybe the professor talking with his head of department here. The professor has scribbled some nice mathematics on the left and some more nice mathematics on the right that obviously proves some interesting conjecture. And then the professor is pointing to the part in the middle, which he's not quite certain about. And in the middle it says, then a miracle occurs. So our job really is to find the miracle that can connect the engine room in the computers that we're using, the operating systems, the things that connect intimately with the implementation of our systems, to the parts on the far right, the interaction with the computers, end-user scripting, computers that present intelligent interfaces that can lead people and teach them how to use the software that they are using in such a way that we do not suffer this explosion in complexity, and that the few core concepts that we use to bridge this far left to the far right remain clear, accessible, and are themselves examples that people can look at, understand easily, and learn from all the way throughout the architecture. So I thought what I might do today is give you an idea, maybe not exactly of the kinds of principles and miracles that we're talking about in the middle, but at least a taste of the kinds of things that we are looking at in the middle. And so the first example is something that everybody here is familiar with, and that's just placing text on a screen. And this has come a long way from the days when we were drawing pixels individually to represent characters in bitmap fonts to what we see today in systems such as Cairo, and in fact many desktop publishing systems that you may be familiar with, where we have beautiful, scalable, arbitrary size, anti-alias text. But the concepts involved really are very, very tiny in that whole domain. And we can reduce it really to just talking about shapes, whether they're polygons or some kind of more complex contour like a Bezier curve. We can choose 1, maybe 2 small graphical primitives, add a few tiny mathematical ideas such as the translation, rotation, scaling, the kinds of affine transformation you can do very easily with a little elementary matrix algebra. Add some stylistic information, color, foreground, background distinctions, etc. And then apply these throughout the entire system. So if you were to take a modern computer interface today and actually look very carefully what each of those pixels on the screen is actually being created by, you will find a plethora, you will find a multitude of different abstractions that are all kind of crowbarred into the same space. So the thing that's drawing the windows, the thing that might be drawing a drop shadow behind something, the thing that's drawing the text, the thing that's making the cursor appear, all of these are really coming from quite different processes within the system, when in fact they should just be all part of a very simple, very scalable, easily understandable abstraction that is applied uniformly throughout the machine. And so if we take the example of text, for example, then just connecting various polygons, you can reduce this to triangles, or you could reduce this to Bezier curves, and then everything that you might want to do with text, including scaling it, rotating it, giving it perspective on the screen, is very easy to achieve. And I will show maybe just 3 very quick demonstrations during this talk. This is one I will not go into in detail, but what I have just described, this very simple set of abstractions and transformations on the polygon or contour abstraction underneath, has been applied to the entire desktop, and you can see that I can type into into this window. Everything you're looking at there, these are not text characters as far as the machine is concerned. They are simply straight lines and Bezier curves that have been appropriately filled by the graphics abstraction. What you get with simplicity, and not just in this example, but wherever you apply it in computer science, when you start looking at simplicity and flexibility together, the kinds of things that become very easy to do are sometimes quite surprising. So I have a little hidden window down here, which actually shows that very same window, but rotated, scaled, and translated. And you can see that if I change the selection in here, it changes up in this window here as well. And this was about 2 lines of code to add to my program, simply because the abstractions I'm dealing with are extremely simple and scalable. So my window is just an object in a hierarchy, and if I choose to make a second projection on that window, there is no accidental intricacy or complexity in my organization that prevents me from doing that. And of course I can type into this little window just as easily as the big window. Other examples of things we can make is a projection of the entire world, so that if we want little thumbnails, but the thumbnails themselves remain active, and I could interact with the thumbnail too if I wanted. So this is just one example of the kinds of flexibility we get by taking small but powerful abstractions and then seeing how we can scale those to all of our interaction with the machine. And of course, after the talk and during the workshop, I would be happy to demonstrate and to talk with anybody who's more interested in this in as much detail as you want. So that was just one example. Other examples that I've picked at random, if we look at typical object-oriented programming languages these days, a lot of the accidental complexity and the intricacy, which is so hard to teach, especially to as a first programming language to freshman CS students, a lot of that comes from inappropriate choice of abstractions in order to solve really quite simple problems. And so things like multiple inheritance really have no place in an abstraction. What we should do is go back to some very early ideas about how to look at objects. And at Xerox PARC, there was a group of people whose instant reaction to an object having multiple roles was not to add multiple inheritance to the system, but simply say, well, an object is multiple things. It has multiple personalities depending on who is interacting with it. And this is a very, very simple thing to imagine and to apply, and a thing that scales immensely well throughout everything you might want a computer to do. And it actually corresponds very well with how you interact with people around you in the real world. I could look at a person sitting in this room and I could think of, biological life form, mammal, etc., respirating, all of the live things. I could think in terms of physical location, orientation, in world coordinates, galactic coordinates, local coordinates, whatever, etc., etc. Or I could think of them as a father or as a child or as a brother, or I could think of them as somebody who owes me 10 euros. Many different ways of thinking, and when I'm thinking about this person in one particular way, all of the others are irrelevant, and so why should they complicate my picture? So this is just one thing maybe that we should go back and rediscover from what has been lost in a simpler time of computer science, where the visions maybe were a little utopian for their time, but have still a lot to teach us in this day and age. Other examples are unbreaking certain asymmetries which have crept, maybe accidentally, maybe because of local constraints, into the designs of most of our programming languages today. There seems to be a dichotomy between the way the functional world does things and the way the object world does things, and from an implementation point of view, it just all boils down to where do you store the tables that tell you what the behavior is when you combine a name with a type. In the object-oriented world, we generally choose to store that information with an object, and we say when this type of object receives this kind of message, then this is the functionality that comes out from there. The functional people, of course, say that's useless, that's a waste of time. What you should be doing is saying, here's the name of some functionality, here's a group of types it works on, so let's store in that name all of the behaviors that correspond to particular combinations of types when presented to that functionality. And that, of course, gives you multiple dispatch and other interesting possibilities which the object-oriented community sadly are missing, in my opinion, inheritance between selectors. Why should one type be related to another when I can just as easily say, if I don't understand this piece of behavior, then don't think about finding it in a different type. Think about finding it in a related behavior. So where we have inheritance or delegation between type, we could also have that between the names we are using to describe behavior. Other things that fall out if we try and reunify these two views of the world, namespaces, capabilities, ways of having incompatible behavior loaded simultaneously into a system, all of these things that in some ways are still research topics start to look very simple to solve. A few random examples of other things that we might want to consider. We're still very much, or at least many of us are still very much stuck in this world where we view a computer program as a list of instructions that tell the data what to do. And this is a way of looking at programming which really does not scale and does not correspond to the way the universe manages to scale. Or even to artifacts such as the internet that we have is maybe the single most scalable technological artifact created so far by the human species. Instead, these things in the real world and in massively scalable, successful massively scalable systems tend to react to things happening in their environment rather than to a list explicitly of commands what to do. And there's been a lot of interesting work done well, actually a long time ago, and then a revival in the last 5 or 6 years in publish subscribe mechanisms, which are one attempt to try to describe systems in such a way. We set up the conditions to react to things happening in the environment and then just let the environment go and change itself as it wishes. And we can trace this all the way back to a very good thesis written, I think, in the 1970s by Fisher. I forget his first name. But the thesis is all about the minimum abstractions needed to describe control flow within arbitrary programming languages. So what do you need as your minimum building blocks to describe any kind of imaginable control structure in programming languages? And of course, this should sound familiar to anyone here because it's very much in tune with the idea of self-sustaining systems. Find small kernels of behavior or of meaning, and then see how they can be used, they can be scaled to describe the entire system. TeX, the typesetting thing, is actually a fully functional programming language built on principles very similar to this. And if you consider that it can typeset a 500-page book on a reasonably new machine in less than half a second, you see that some of the ideas, the mathematical ideas that are employed low down in the system, scale very, very well. I'm not sure how long it would take Microsoft Word to format a 500-page document, but I'm guessing it would be more than half a second. Another thing that we are curious about is why does the network stop at the boundaries, the physical boundaries of the machine? Even though some parts of the internet are horrendously complex, if you look at the protocols for gateways and routing information to be exchanged between machines, these protocols really are quite nasty and disgusting and horrible to write and even worse to debug. But there are some properties of the internet, especially when it comes to resilience, to fault tolerance, some properties that are almost inherent in the way that you program, especially using unreliable transmission protocols, that could teach us something about even smaller objects, more fine-grained communication happening within our machines. If we were to treat every object, even an integer, as a little miniature node in our network, and so we're not always sure if we say 42 plus 1, whether that's going to arrive at our integer, and we're not sure whether we'll ever get a response, and we're not even sure if that plus will come before or after the thing we asked it to do next, how would that affect the way we look at the construction of our programs, and would it make them more scalable, more reliable, etc.? I don't know, but this is one of the things that we will be looking at, and I think is interesting for anybody in computer science to be thinking about. Another thing that falls out of this is the idea of asynchronous dispatch, decoupling the time you ask an object or you modify an object's environment from the time that object reacts to this. And we have seen systems recently that employ similar ideas to scale in distributed, parallel, concurrent contexts where ideas about time and looping are made much more explicit than we are used to. And instead of treating a message to an object as an immediate command to do something, you treat it as a request for something to happen sometime in the future. And something I'll return to briefly in a little while are pattern-directed transformations. These crop up everywhere in computer science, from language theory to artificial intelligence to many other domains, compiler construction, all the way from the input text to the generation of instructions at the bottom. And inference mechanisms, which are very closely related, I think have a lot of power, a lot of mathematical simplicity and scalability that really has not been applied to good effect or used to the scale that it should be deployed within a computing system. Those are a few tastes of the kinds of things we're looking at. There'll be one or two more examples in a few minutes. But let's, before we forget it, go back to the list of software systems that we began with and take another look at GTK. One thing I was very surprised to read in the 2.0 release notes for GTK was that they seemed to be quite proud of the fact that they had managed to double the number of lines in their source code from the version 1.2 release to the version 2.0 release. I don't really have any great, deep, profound thing to say about this, except just to pose a question as to why is it in the mentality, at least of some part of the computer science community, that adding lines of code to add functionality is an achievement, when really, from my point of view personally, and I hope if you think about it, if you're not already convinced, you should see that removing lines of code whilst adding expressibility, functionality, reliability, etc., should be the commendable outcome of your efforts. I have some reasons why really their system is 2/3 of a million lines of code. Mostly it comes down to, I'll try and be brief because we're running out of time, mostly it comes down to the rigidity of the runtime system they're using, the programming language that they chose to use, and in many ways, a surprising number of ways, even to the surface syntax that they choose or are required to use to interact with those systems. And many tens of thousands of lines of code, if you go look at how GTK is constructed, tens if not hundreds of thousands of lines of code have been lost simply because they are battling with inadequate means of expression because of the choice of programming language and the paradigms and abstractions that come along with that language. And this has many repercussions throughout the system. So one I call a vertical catastrophe is that the rigid substrate that they chose to build all of this upon makes the top end not only complex but rigid as well. The rigidity that you start with at the bottom either requires a horrendous amount of work to overcome or simply will pervade the entire system. And then a horizontal catastrophe is that the sheer volume of that code, 600,000 lines, were already were well beyond a textbook's worth of information in there. The sheer volume of that imposes an unrealistic learning curve if you wanted not only to understand in general how that system is built, but specifically why every line of code is the way it is within that system. The learning curve is unrealistically large. So this effectively closes the system to your understanding of it, and if you don't understand it, how can you be sure that you're adapting it correctly, and how can you really innovate in interesting ways within that system, unless you are a particular kind of power user that can very quickly isolate and understand small parts of the system that are interesting to you. But the numbers of people on this planet that can do that are fairly small, and it certainly will not scale in another dimension to the majority of people who are using and may be dissatisfied and want to modify that system. One more thing I'd like to mention is that a problem with the languages that are chosen frequently for these systems, such as C, is that they cannot possibly predict the kinds of expression people want to bring to the solutions that they are constructing within those systems. And so one reason they take so many lines of code in GTK to say so little is because, well, not only is the system inadequate that they chose, but is also not designed to scale with new means of expression or new paradigms that they want to bring to their solution. And in fact, if you think about it, it becomes clear that it's impossible really for anybody to predict the kinds of expression and the kinds of paradigms we will want to be using in the future. And Einstein said this, that this is the sentence that's widely misquoted as everything should be as simple as possible but no simpler. What Einstein really said was a little more interesting, in that when we create systems with empirical content, and certainly computing systems, programming languages are systems with empirical concept, then the irreducible elements within that, and if you think of an irreducible element as being the type system that you're using or the semantics of the operations within your language, then those should be as few in number as possible. But the important thing is not to renounce the representation of any future empirical expression within that system. And it's this last part, I think, that computer science has yet to really sit up and address. So from our point of view, how are we going to do things differently? Well, we're not going to try and predict what people will want to do with our system once it's up and running, but instead come back to the self-sustaining ideas and the topics, some of the topics of this workshop, which is to provide a few minimal abstractions, but abstractions that are chosen and implemented in a very, very particular way, in particular in a way that means that no new paradigm is precluded from being easily added in the future. And then within this system that is very, very open and allows anybody to modify any part of it, everything becomes extremely late bound. And by late bound, I mean extremely late bound. I mean much more than for example, in Lisp or in Smalltalk or similar languages, where you have a very high degree of late binding, but it stops at a certain level. It does not go all the way to the floor, to the silicon underneath the implementation of your programming language. In some Lisp systems, and certainly in all Smalltalk systems, the vast majority of Smalltalk systems, that stops at the virtual machine, at the the monolithic piece of impenetrable stuff that causes the semantics of your program to be executed at runtime. And from your user's point of view of consoles or of objects and messages, it is actually impossible to cross that barrier. So immediately, parts of the system that are implemented underneath that, the semantics of your language, the runtime interactions with interesting parts of the system, are closed off for you. And you either have to be a special kind of wizard or know a special kind of wizard to go in and perform root canal surgery, really, at that level to make the system do what you want. A traditional programming language, and this is absolutely true of all fully compiled programming languages, and is to some extent true even of the very dynamic languages, is that we have certain parts of the system artificially closed off from us. We can write some source code, we think we know how that source code causes the application to behave, but the stuff that really increases our expressivity and our power to interact with the system are the semantics of what we are writing. Can we extend those in meaningful and deep ways? The syntax, how can we express ourselves very succinctly? How can that be then easily converted into instructions for a compiler and the runtime? But all of this is hermetically sealed in most systems. So an extremely late bound system would move all of that outside of the box and into the user land, such that a sufficiently motivated user, and once you come across one of these barriers in your programming language, you very quickly become motivated to try to do this kind of thing. A sufficiently motivated user can go in and say, well, my semantics is a little similar to this, let's see how this was implemented in the language. And if we've constructed the system correctly, the system should be a curriculum for system construction, and by looking at how something similar was constructed, it should be become obvious to maybe not the vast majority of users, but certainly many more users than are those wizards that can go in and modify a virtual machine, it should become apparent how they could maybe experiment and finally, with a little work, find out how to implement the new semantics of their system, or the new pragmatics, the interaction with the outside world, or the new semantics, a way of, my example in C is always, I love anonymous functions. Writing lambda is my favorite thing to do between parentheses, but I can't do it in C. And there's no reason, because the semantics of the language completely embody that. It's just that the dumb compiler says you have to give it a name and declare it outside of your argument list. Drives me crazy. So, the way we're approaching this at the very left end of our diagram, the very lowest level of our system, is constructing a thing I call the combined object lambda architecture. There are two parts of this, and they're combined because when I began thinking about language implementation, I love Lisp, and there was a chap called Kelsey, I think, Richard Kelsey, who once posited a thing he called pre-scheme. And this was a way of implementing Lisp by saying, hey, let's keep the nice things about Lisp, but change the level of semantics at which we are talking. And if we can talk about pointers and memory allocation and interaction with the operating system in our nice language, it's very easy then to create the higher level and the safer data types and operations and abstractions on top of that. So that's very nice, and it has some of the same characteristics that we find in McCarthy's papers and in the Lisp 1.5 manual, where there is a half a page of code that implements the Lisp system in itself. Kind of. Because what's always missing there are a few small primitive operations that are always taken for granted. In McCarthy's case, it's the 5 elementary functions that he talks about, cons, car, cutter, and a couple of others, which are just given to you as fundamental axioms within your system. So how do you start talking about those in an abstract way if you do not have the means to describe them within your system to begin with? Well, one way is to treat those as objects that respond to messages. And the objects are a nice scalable paradigm in which to work. Message passing scales in different ways to function application. But there are also problems with object and message systems in that they too, in a way maybe more severe than Lisp, are incapable of describing their own implementations fully. However, so if we think of the Lisp world as describing how behavior comes into being, how functionality works and how functionality can be reasoned with, and the object world as being abstract types and how we interact with abstract types and the protocols that they export for us, if we bring these two together, we can think of one being function and one being form, and neither is complete without the other. So what might happen if we bring the two together? And this is what combined object lambda architectures are all about. In this diagram, we'll start from the object side. In this diagram, we see a way of representing a data structure. It might be an S expression, it might be an end-user data type, it doesn't really matter. And to interact with it, we send messages and expect responses from it. And that's a very simple story. Take an object and a message, and that gives us some implementation of a method. And the method itself is just a sequence of other objects receiving other messages. And that's the end of our abstraction. That's all there is to understand. But there are some mysterious things in here that we haven't really explained. One of them is this combination operation between the object and the message. How does this actually work? Our objects and message paradigm is incapable of describing the internal workings of that. The second thing is the sequencing of these further message sends within the implementation. How is that sequencing of sends accomplished within the implementation of the method? Again, objects and messages are not sufficient to completely describe how that works. However, if we have something else in our system that is just pure function, pure behavior, we can very easily use that to construct a piece of behavior which, let me just skip ahead a few, construct a piece of behavior which does represent either that implementation or that combination. In the case of objects and messages, the dynamic binding and then the application mechanism that sends a message to an object. So we can use the objects to create data structures, and the data structures themselves maybe look a little like S expressions and are transformed down into something that is binary executable code or some executable representation for the system. And then at some level, well, at all of this level, we are out of objects and messages and into pure functions, but at the very bottom, what we get is some pure function that can be used as the missing implementation in our object system. And the thing is completely symmetric. We can also look at it from the function side and try to do a McCarthy exercise on it to describe it in terms of itself. And when we hit that thing at the bottom that says, how do we store the very primitive data types within our system, we just appeal to them as objects, and we say, we send a message to it. And then later on, when it becomes clear we need to know how to implement that message sending, we say, hey, we have that functionality already because that's what we began with. So these two paradigms can complement themselves in such a way that the system can be entirely described from within without needing any external support whatsoever. Whilst remaining within those two very small, very scalable paradigms without having to resort to any kind of magic whatsoever. So we take this idea and then scale it in all directions from the parsing of the input or the user interaction on the screen from the user, all the way to the implementation on the right, and then upwards to the interface with the operating system. We can parse the header files and talk to the binary files of the operating system, the libraries, and then downwards into creating, and this is where it starts to get interesting, the domain-specific languages for better expressing the solutions to our problems, or maybe the application-specific languages, or if you have a 3-line region in your program where you want to talk about a particular mathematical concept, maybe it's array multiplication just by saying capital A next to capital B, then it should be possible to construct a mood-specific language that is in effect just for that very small part of your program where suddenly the rules of algebra become matrix algebra rather than scalar algebra. And so what's important here is that everything is really just objects and functions combined according to pattern-directed transformation. And pattern-directed transformation is something that is fairly easy to teach as long as it's kept simple and you don't worry about some of the more esoteric implementation mechanisms of it. If you present it at face value, BNF, extended BNF, etc., people tend to grasp it very quickly. And so here is an example of the complete grammar for a grammar definition language. And it's just over 1 page, 1.5 page of code. And I can use this language to create other languages, but I have bootstrapped myself in my grammar definition language into a system that's very powerful now, because the next language I create doesn't have to be anything remotely resembling the language I began with. And so this is now the third page of code we have looked at for this pattern-directed transformation chain, and this third page describes what an ASCII art diagram means. And we've all seen ASCII art diagrams. If you've looked at the way the network protocols work, the RFCs, in there are these beautiful little teletype formatted diagrams of what's inside a packet and what does each of the fields mean and which bit positions do they occupy. And there is actually a semantics inside that diagram, and we can express it in a few lines of code like this, which means that suddenly in our system, what I'm showing on the slides now becomes an executable program. I can feed this to my system, having taught it how to interpret an ASCII art diagram, and what it will construct for me is all of the accessor functionality needed to deconstruct and reconstruct an internet packet. And what you see below is a grammar. I won't show you the rules around this, but a similar idea can also be taken not just in the space domain, but in the time domain. And at the bottom, you see a grammar that describes how TCP protocol, or at least a simplified version of TCP protocol with some of the esoteric stuff removed, how that can actually be represented in 7 lines of code. And this actually really works. And the second example I wanted to show you, I have to type in the root password because I'm going to make a network tunnel here. So this has actually parsed exactly the program that you see over here with a little bit of context around it to make it mean something. And you will see as I open a web page onto my newly created tunnel, it's printing out the contents of the packets that are flying past on the left. And this is maybe 120 lines of code that implements a web server that is happily telling me over here the current time and date when I refresh the page. So that is a very real piece of functionality expressed in maybe 3.5 pages of code. If you were to try that in a traditional programming language where you don't have access to semantics, you don't have access to syntax, it would, I'm guessing, take you quite a few more pages of code to express. Okay, this scales all the way from the far right of the diagram, the miracle diagram with the yellow blob in the middle, scales all the way to the left, to the implementation side. We can look at the problem of generating maybe not optimal, but at least very high quality code for a modern processor as a pattern-directed transformation. It happens to be one that's going in reverse. Normally you start with unstructured text and you parse it into a structured representation your compiler can understand. But the process is completely symmetrical, and the mathematics that describe it is completely symmetrical. It could care less about which way t goes. And you can use grammars to describe how to recognize structure within your data and construct unstructured output from that. And one interesting unstructured output we can generate are machine instructions. And for anyone who's interested in this, the most famous example was the LCC compiler, which was Hansen and Fraser, I think, did that work. They created a thing called Elberg, which is a bottom-up rewrite grammar, but it's exactly the same, in essence, the same kind of grammar that just parses your programs and feeds them to a compiler. And there are a nice body of papers on the theory and the implementation of this. When you reduce the theory to its simplest form, it turns into about a 15-line program that is capable of generating some very high-quality code for modern-day processors. So we have this pattern-directed transformation within our combined object lambda architecture that's taking user interaction on the left and creating some executable stuff on the right for a target platform. And the transformations at each stage are first class and dynamic. You can modify them at any time that you want during the running of your application. They are first class in that you can that they have no pre-imposed restrictions on what you can do with those things as program values. You can treat them like any other program value. But what you can do with this is optimize your expressivity at each level within your system to match the domain or the activity that you are trying to work within. So how far could we take this? Could we really arrive at some Maxwell's equations for computer science? We don't know. We think that probably that's a 50-year research project, not a 5-year research project. But the kind of expressivity is already familiar to most computer scientists who've done a little bit of logic in their training. And if we look at mathematical logic, it makes statements such as P implies Q, which most people read if P then Q, which is not quite implication, but it'll do for today. What's interesting about this is the domain of P and the domain of Q. And what the philosophers and the logicians quickly realized is that they can reason about the system within the system. And so the algebras that they're constructing for their mathematics also become algebras in which the mathematics and the algebras can be discussed. So if we say P implies Q does not necessarily mean that Q implies P. We have used the system to make a statement about the systems. And this is the kind of thing we think we can arrive at within 5 years. It may not look as pretty as Maxwell's equations, but it should look a lot prettier than the kind of mess that most programmers and most end users are dealing with today. And we've built a few systems that actually run real programs right now using this kind of reduced to the essence approach. And so we have a JavaScript, a Prolog. We're in the process of building CodeWorks, which some of you may, some people in the audience who have grey beards will remember CodeWorks. And we're building these systems in literally a few hundred lines of code. Because not only can we play with the semantics and the syntax of our system, we can modify the way data is stored in our system and the way that data and the functions behave at a very low level. And we can do that very, very easily within the system because everything is extremely late bound, malleable, and first class open to us to experiment with. So some other things we've built very easily. Anyone who's seen eToys will recognize the graphics that are producing this. This is how to make a cat bounce around the screen using data flow. And data flow is it was popular in the 80s for a while as a research topic. It's maybe not entirely gone away. But data flow is interesting because instead of concentrating on what your data should do, it concentrates on the relationships between your data. And it makes explicit a notion of time. We're going to feed some inputs into this, and if you notice on the right, the outputs are named the same as the inputs. So we have a systolic system where there is an explicit notion of a clock ticking. So we feed the right-hand side back to the left-hand side every time the clock ticks. And this tiny program will actually make the cat bounce around the screen. Another example that we like a lot is looking in the real world, in physics in particular, many of the theories are talking about particles within fields. What's interesting there is also that the messengers within a field that caused a field to exist themselves are particles. And the quantum guys insist that the particles even are themselves just little waves which are kind of field-like. But if we pull this back into computer science, what we see here is a part of what might be a very simple text editor. What's different about it, though, is that there is virtually no global information whatsoever. What you see, each of those letters is a little object that only has two goals in life. Each one of those objects knows who its predecessor in the sentence is, and its goal is to try and be immediately to the right of its predecessor, except when it flows over the right-hand margin of the page, in which case it tries to go to the beginning of the next line. So the location of the right-hand margin is the only piece of global information in this entire thing, and if you set this up, jumble the letters at the bottom and let it go, the letters will spontaneously organize themselves into a nicely filled paragraph. And if you look at some of the algorithms in word processors that try to do this, they are much more complicated than the 10 lines of code it takes to describe this when you start thinking about it as a particle within a field rather than here's a data structure, let's find the best points within this data structure to start splitting it into substructures. So I promised I would eventually come back to Maxwell's equations. I'm going to go 5 minutes over time in this, but only because the introduction was a little over time. If we go back to Maxwell's equations, one thing that I think is a very, very, very important lesson, especially for all you students of computer science sitting in the room right now, a very important lesson is that if you want to see further than those who have gone before you, you are at a great disadvantage if you choose not to stand on their shoulders. So find the giants that have done amazing things in the domains that interest you and then completely embrace what they have done to make your contribution to the field. And Maxwell is a beautiful example of this. If we take Maxwell's, in quotes, 4 equations and see who actually came up with them, we find that the first one was due to, in fact, the first 2 were due to Gauss, not Maxwell. The third was due to Faraday, not Maxwell. The fourth was due to Ampere, not Maxwell, although we have to admit Maxwell corrected a slight inaccuracy in it. But what Maxwell's contribution was to recognize that these 4, or actually these 3 separate pieces of work within the domain of physics, which had never been brought together before to try and coherently describe a much simpler but more powerful way of looking at something, these 3 things were intimately related. So his contribution was to take individual pieces of work, bring them together and see what the combination was capable of doing. And it's interesting, if you go and look what Einstein did for special relativity, there's a very, very similar story in the mathematics behind relativity. And so here is just one page that describes some of our giants most closely related to the combined object lambda, that part of the system that I have talked about today. And we could maybe find, if we thought about it, another page of giants from computer science. And a lot of this work was done in the 1960s and the 1970s, and the computer science community has a terrible memory. It has some sort of a group amnesia, it seems, and every 10 years has to reinvent the wheel. Maybe that's the way research funding works, I'm not quite sure. But as students of computer science, I really, if you haven't done it already, I really encourage you to go back and within your particular domain of interest, look at the work that was done in the 60s, look at the work that was done in the 70s, maybe even in the late 50s. Because the people who were working in those domains were rigorously trained scientists, usually either electrical engineers or mathematicians, and they were working within constraints that are absolutely draconian compared to what you have today. And so the solutions that they thought of were beautiful pieces, little gems of inspired science, inspired real mathematics that have a lot to say about the mess we find ourselves in computer science today. So please, go back and become an archaeologist for a couple of months and be astounded by those little gems that you will discover in the history of our science, so-called science. So I'm going to finish today really by saying just a few things about fresh perspectives as well. Once upon a time, memory was fast, processors were slow, and the processor speed limited everything really. So people went to a lot of trouble to try and calculate something once and then remember it. So caching was born, memoization was born, etc. And then processors got faster, memory got a little bit faster, but anyone who's tried to build a PC will know that it's not the processor anymore that's the bottleneck, it's really a front-side bus. And the memory bandwidth and that front side bus really limits the performance of what the machine can do. However, the processor itself is sitting idle most of the time. So if you have some mathematics that previously was considered too expensive for your solution, go back and think again. Maybe we should just do the math these days because the processor's not doing anything else. So forget the ad hoc stuff and do the math for real. And one thing that we have already done in this direction is to look at the problem of 2D rendering in the sort of PostScript tradition of 2D rendering, where we don't consider it the same as just a special case of 3D, but go back and look at the same kind of math that the PostScript guys were doing at Xerox and at Adobe Systems. And ask ourselves the question again, what does it mean to try and render a list of polygons with anti-aliasing, etc., onto a frame buffer? And it turns out that instead of looking at this as an oversampling problem with lots of caching and optimization going on in a horrendous pipeline called Cairo.o, if you look at it instead of the mathematics and you ask yourself the question, here's a pixel, here's a list of polygons, how do those polygons influence this pixel? What falls out is less than a page of mathematics. How does this scale? You can implement this in less than 100 lines of code. And very quickly, I will just show you, if I can find the window, I'll very quickly just show you the result of that. What you are seeing now is the mathematics on the right drawing 60,000 Bezier curves per frame refresh on the left. And that's going pretty good. One of the things we'd like to do in the near future is to see how extensible our system is on the left-hand side, and can we push some of this computation either into FPGAs or maybe onto GPUs, or more interesting is the new class of hardware, graphics hardware that's coming out, where instead of shading hardware, they have stream processors, and these really are little miniature general purpose CPUs sitting idle for most of their time. So if we take the math on the right, which is beautifully parallelizable because it is mathematics, and we apply it to our 1024 stream processors on the left that are otherwise sitting doing virtually nothing, just how fast would this go and just how scalable would it be for our one page of mathematics and less than 100 lines of code in the real world? Which, of course, if you've understood what I've been saying today, isn't always going to be the case, because eventually the program should be the mathematics on the right. So, am I wrapping up yet? Yes, okay. So to wrap up, let's try and put this in the context of self-sustaining systems. So the call for papers talked about systems that can bootstrap, implement, modify, and maintain themselves. The thing that I have done, thing I've described today, can do all of these things, in part because it's all extremely late bound. It has a minimal kernel, and you can add to that either comprehensive reflection or complete metacircularity. In our case, we choose complete metacircularity. Without stepping outside our paradigms, we can go all the way from the interaction with the machine down to the implementation, maybe even into the silicon. So small number of very powerful abstractions uniformly applied throughout the architecture that creates an architecture that is the engine of its own replacement, and you can even think of it as a laboratory for its own future. So that's really the topic of the workshop. What I would like to suggest is that while we're all gathered together for the next day and a half, we also start thinking about the larger picture of self-sustaining systems. And again, let's bring this back to nature, and in particular how biology works. And if you think about it, human beings have two things. They have a condition which will never be fixed, but they also have a species. And the human species is something that has existed for many, many tens, hundreds of thousands of years. So the species is a self-sustaining system. And you could think of it as a global system. But the individuals within it are mortal. They tend to die off. So the system is much more than the individuals that represent it, but a system such as a species cannot survive unless it is adaptable and prepared to change. Environmental changes happen, natural catastrophes happen, supplies of certain kinds of food die off for other reasons, etc. So a species, and I would argue a computer system or a paradigm within computing must respond not only to internal pressure, advances in implementation techniques, but also to external pressure, changes in requirements. You can't call up IBM these days and ask for a System 360 to be delivered tomorrow. So if your software runs on IBM 360, you already have a problem, but it's not your software that's the problem, it's the environment around your software that's the problem. So local death is vital for global survival. And we can see this in computing as requirements change, environment change, and paradigms change. I'm sure there are going to be exciting computing paradigms. We've seen logic, we've seen pure functions, we've seen sub-paradigms like single assignment, etc. All of these little things that have been brought to computing and have made incremental changes to it. We're not done with those yet. So we must learn in our self-sustaining systems to be ready to make little local pieces of mortality, little local things die off, so that the overall system itself can continue to evolve and to survive. And I call this paths to migration. If you take a system, it either learns how to migrate to adapt itself to the future, or it will die. And so if you want the things you're building and you're going to build in the near future to be self-sustaining and to outlast their creators, please, from the very, very beginning, build in self-sustainability, self-modifiability, bootstrapability, and make the things you are creating the engines of their own replacement. They have to die, but if they can be replaced from within, you've already won the survival of the species problem. And this is surprisingly and maybe even acutely relevant to interpreted languages, languages running on virtual machines, where generally we create a zone of comfort above, which is the abstraction in which the users are operating, and then a virtual machine implementation, which is ugly and disgusting and contains other kinds of horrible, unmentionable programming languages down below. But the fact that we have these two completely inseparable things, not only do we have that barrier to expressivity there, we also have a barrier to evolution and a barrier to migration, because the users cannot evolve without finding somebody to cooperate in the evolution simultaneously of the bottom end. If we can take the self-sustaining ideas, the meta-circularity ideas, implement the system within itself all the way to the hardware, then maybe we create little zones of comfort on top, but they no longer are impenetrable. And we can imagine sufficiently motivated users, which eventually will be most of them, looking beneath the dotted red line to try and find a way out, a way to migrate away from their problems and to evolve the systems that they are using towards even better things. And so I hope that's inspired a little bit of discussion for the next couple of days. These are subjects I'm passionately interested in and would love to drink a lot of beer with you over this evening, tomorrow, whenever. There are a few URLs here for the downloading of stuff, which I will put up during questions. I should also like to thank, we have very generous grants from the NSF that are supporting our work for the next 5 years, but also we have friends, in particular at SAP, that have been very generous, and Nokia and Intel are interested in our work and have been financially supportive of it as well. And we hope, maybe in our own small way, we can affect in a positive way the futures of some of these people. So thank you very much for listening, and if you have any questions, I will be delighted to try to address them.